Okay, let's begin with the following lecture by Balibanu. We're starting at 11:40, so you have an hour.
Okay. So let me begin directly by reminding you where we ended on Tuesday. So G was a semi-simple complex algebraic group with trivial center. I'm going to wait a little bit so everyone has a chance to sit down, or else. Okay, so G was a semi-simple algebraic group with trivial center that we said we often think of as being PGLN, and factor G was its Lie algebra. So in this case, the special linear Lie algebra matrices with determinant 0, and I want n during this talk to denote the dimension of this group. And then what we did was we constructed this wonderful compactification of G, which we denoted by G bar. And inside it was living the boundary divisor D, which was a divisor with simple normal crossings. And on Tuesday, we saw that there's a short exact sequence of vector bundles over G bar, where the log cotangent bundle of G bar goes into the trivial G cross G bundle over G bar, and then onto the log tangent bundle. And this is just a logarithmic sort of infinitesimal action map, where every element of G cross G induces a logarithmic vector field on G bar, so a vector field that is tangent to the boundary divisor. And moreover, we saw that there's a non-degenerate symmetric invariant bilinear form on G cross G that takes a pair x1, x2, y1, y2, and outputs the killing form applied to x1 and y1 minus the killing form on G applied to x2 and y2. And we saw explicitly on Tuesday that this log cotangent bundle is sitting inside this trivial G cross G bundle as a Lagrangian subbundle. And in fact, a subbundle whose fibers are Lagrangian subalgebras. Okay, so let me say a couple of things about the fibers of this log cotangent bundle, because we're going to be interested in them today. So a remark is that while this is a vector bundle, as a bundle of Lie algebras, it's not locally trivial. So the fibers over the boundary divisor are not isomorphic as Lie algebras to the fibers over the open dense copy of the group sitting inside G bar. So for example, we saw that the fiber of the log cotangent bundle at the identity element in the group is just the diagonal copy of G sitting inside G cross G. But then when we were discussing the boundary structure of the wonderful compactification, we said that divisor components are indexed by integers from 1 to L, and that G cross G orbits are indexed by subsets of these integers. So whenever I take a subset J of the integers from 1 to L, I'm going to get a G cross G orbit called OJ. In the boundary divisor. And it is reasonable to ask, what do the fibers, these Lagrangian subalgebra fibers, look like over points of this G cross G orbit? And the answer to this is that if I take the subset J, then I have associated this data of parabolic subgroups and Levy subgroups that we saw, I guess, last time also. And these all have subalgebras, so I'll have a pair of parabolic subalgebras, Pj and Pj minus, which again you can think of in SLN as being a subalgebra that looks block upper triangular, and then it's transposed, its reflection across the diagonal. And I have a Levy subalgebra Lj, which is the intersection of Pj and Pj minus. So in SLN, this is a block diagonal subgroup. And if I take a point, I don't know what to call it, AJ, in this G cross G orbit OJ, sitting inside G bar, the fiber of the log cotangent bundle at AJ is going to consist of pairs of points, one in Pj and one in Pj minus, that have the same component in Lj. So if you think of this as matrices, it will be a block upper triangular matrix and a block lower triangular matrix that agree on this intersection. So they have the same entries in the middle. And in particular, if J is the empty set, then we saw last time that these parabolics are just Borel. So these are upper triangular matrices and these are lower triangular matrices, and their intersection consists of diagonal matrices. And this is going to be I put an isomorphic sign. Isomorphic to the subalgebra of G cross G that consists of pairs of something in the positive Borel and something in the negative Borel with the same eigenvalues in the same order. So in particular, what you see with a little bit of work is that as Lie algebras, these fibers are not isomorphic to G. One way that you can see this is that this is a semisimple Lie algebra. Whereas these guys are not semisimple. fact, they're not reductive. And the reason, one way that you can see this is that they contain, for example, normal unipotent subgroups. So I'll leave this as an exercise to find those subgroups and to remind yourselves that something like that stops the group from being semi-simple. Any questions? So we should, this is living as a subalgebra. I'm being a bit sloppy with my notation. So you should think that this is living as a subalgebra of G cross G, right? So if we tried to write down, I could write B as being a sum of a nilpotent subalgebra and this T. And I could write B minus as being a sum of an opposite nilpotent algebra and also this T. And then what does this subalgebra look like as a subalgebra of G cross G? It looks like a sum of, here I want to have nilpotent things plus diagonal points that are in the torus plus opposite nilpotent things on the right hand side. So if I was going to give a kind of triangular decomposition of the subalgebra, but this is not, I mean, these guys interact, right? So when I bracket something here and something here, I don't get 0. I get something in here, in fact. And these, so this is a nilpotent. It's nilpotent because if I bracket it with itself enough times, it becomes 0. And it's an ideal because it commutes with this guy and it's normalized by this guy. And now we've written down why this Lie algebra fails to be a semi-simple algebra. More questions? Okay. Okay. So.
Question on.
Oh yeah.
So Sarah does ask, are these description of the log cotangent bundle of the boundary easy to see? Can you explain a little bit more?
I think the answer to this is they're not that easy to see. So you have to, in order to see this fiber, what you have to do is think that these, to think of what these fibers look like in the Grassmannian, and then kind of begin with the fiber at 1 and kind of transport it towards the boundary using like the action of a 1-parameter subgroup. And then as you approach various boundary points in various orbits, your Lie algebra that you started with in the Grassmannian is going to tend to a different point that's going to correspond to this. But this takes a bit of work, so you actually have to write down some computations. I don't know like an intrinsic reason why I would just write this out and say this is why it's clear that this is what the degeneration should be, and then everyone would just agree. But I can give a reference for places to find the computations, and there's nothing like that high tech about them. It's just so if anyone would like references for things that that I write on the board, they're welcome to email me and I can provide them. Any other questions? Okay. So what we get from the story is an assignment where to every point in G bar, I can associate a Lagrangian subalgebra. So in particular, I get a map. Morphism of algebraic varieties from G bar into the Grassmannian of n-dimensional subspaces of G cross G. And it's another fact that one has to check, and that is not hard, but also not trivial, that this is an embedding. And then what you notice is that this actually lands in a kind of distinguished subset of the Grassmannian, which is the subspace consisting of Lagrangian subalgebras. Of dimension n. And this the space of Lagrangian subalgebras is what I would like to talk about next. Any more questions? Okay, so let's sort of move away from the setting for a second into a more general setting. So let factor D be a 2n dimensional B algebra. It could be over the real numbers or over the complex numbers. And I'll assume that it comes equipped with a non-degenerate, symmetric, and invariant bilinear form. And then we have a definition that the variety of Lagrangian subalgebras of D is just noted fancy L of D. It's just the points in the Grassmannian that correspond to Lagrangian subalgebras. So this is living as a subset of the Grassmannian of n-dimensional subspaces of D. And in fact, both the condition of being a subalgebra and the condition of being Lagrangian are polynomial conditions. So this is a Zariski closed subset of the Grassmannian. But it's possible that it won't be a submanifold, so it might not be smooth, it might be singular. It often is singular. And it might also be disconnected. And of course, if D is a group integrating this Lie algebra factor D, then the action of D on this Grassmannian preserves this variety of Lagrangian subalgebra. So this is a stable subvariety of GR. Did I write? Oh, yeah, that's good. Okay. Okay, so motivation. To study No, I don't think I'm assuming anything about it. Then that would not be very interesting, but But in principle, I mean, that's fine. I guess, yes, I could add this assumption to make sure that this variety is non-empty. Okay. So motivation to study this space. Suppose that I have a Lagrangian splitting of D. So this is a splitting into a direct sum of L1 and L2, where L1, L2 are Lagrangian subalgebras. And if that's the case, then the triple DL1, L2 is a Riemannian triple, like you saw yesterday in the problem session. And in this case, I'll denote L1 by U and L2 by U star. So this is Riemannian triple. And then on U, for example, I get the structure of a Poisson Lie group. Which I'll call U pi U. So here's the definition, which briefly came up on Monday in Enrique's mini course. We'll say that a Poisson manifold M pi is a Poisson homogeneous space for U. If it's a homogeneous space, so if U acts on M transitively, and if the action map is a Poisson map. So here U cross M has the product Poisson structure, and M has pi. And in this case, for any point in M, I can extract, first I'll let UM be its stabilizer in U, and little um be the Lie algebra of the stabilizer. And then at every point, and then at the point M, this Poisson structure is a bivector, so it's living in the wedge squared of the tangent space of M at M. But this tangent space I can identify with U modulo this stabilizer subalgebra. And this means that by contraction, IM gives me a map from U mod UM star to U mod UM, which I'll denote by pi M sharp. And using this map, I can define a subspace LM of this Lie algebra D as pairs X and U and Xi and U star with the following properties. So first, Xi restricted to the stabilizer subalgebra is 0. So this means that Xi descends to an element of U mod UN star. And then I can require that when I apply pi m sharp to this element, I get the coset of X.
What does differ X sign mean?
It means that I take a Lagrangian splitting of D, and then I name my factors U and U star, because when I have a Lagrangian splitting L1 plus L2, then L2 is canonically identified with the dual of L1. And then I can think of D as, well, as a set. It's a direct sum of U and U star. That's a Lie algebra. It's usually written with this kind of bow tie notation that maybe appeared yesterday. But in any case, an element of D is an element of U and an element in U star. And then for elements of U, I use X, and for elements of U star, I use Xi. Okay, and theorem. This construction is due to Drinfeld from sometime in the early 90s. And theorem says that the subspace Lm that I've defined is a Lagrangian subalgebra of the Lie algebra D. That this assignment is equivariant with respect to the action of U on M. So if I take the Lagrangian subalgebra corresponding to the point U acting on M, this is the same as taking the Lagrangian subalgebra corresponding to M and then transporting it by the adjoint action of U. So in particular, this means that the map P sending M into the variety of Lagrangian subalgebras through this assignment is equivariant with respect to the U action. And the third part of this theorem tells us that this assignment gives us on some level a correspondence between Poisson homogeneous spaces of the Poisson Lie group U and U orbits in this variety of Lagrangian subalgebras. So let me say that the assignment, when I take a Poisson homogeneous space M pi and I map it to the U orbit of Lm for any little m and m, is an injection once I restrict to the set of Poisson, how do I want to write? Poisson homogeneous spaces with connected stabilizer subgroups UM. And to each such Poisson homogeneous space, I associate a U orbit. On LD. And this shouldn't surprise us, right? Because we're associating to M pi the orbit of this LM, but LM is defined only sort of on the level of Lie algebras. So LM only knows about the Lie algebra of the stabilizer. It doesn't actually know whether the stabilizer has multiple connected components or not. So this is kind of the minimum condition you would require to restrict to in order to have an injection. And the image is the collection of Lagrangian subalgebras with the property that the intersection of the subalgebra, which again is the subalgebra of D, with U, which is now covered, but is also a subalgebra of D, that this intersection integrates to a closed subgroup. Okay. So I put on the problem sheet a couple of exercises that lead towards this second dash. So towards seeing that the image of this injection actually consists of only of subalgebras with this property and hits all subalgebras with this property. And so the theorem of Trinfeld gives us correspondence between Poisson homogeneous spaces and U orbits on this variety of Lagrangian subalgebras. Let me pause for a bit for question.
Would you find also without having a complement?
Without having a complement.
This side doesn't really have it as a complement, so it's one word, but the other side.
Which side do you mean? Like this side of the embedding?
No, I'm thinking if you start with the D.
Uh-huh. Mm-hmm.
Talk about this side, but on the other side.
Yes. Yes. I think that there are also I think there are also sort of actually very interesting things that one can say when you take like maybe a Lagrangian complement that isn't a subalgebra and things like this. But I don't know if I'll be able to say anything right now. Okay. So what I want to say next is that yes. Yes.
Is part 3 of the theorem due to Trinfeld or even so?
I thought that part 3 of the theorem was due to Drinfeld, but if Liu thinks that it is due to Evans and Liu, then he's probably right. So maybe on the bibliography, I defer to him. And everything that I'm about to say from now on is due to Evans and Liu. So for the rest of today. And what I want to say is that sort of first, the important thing to say about the setup is that we have this map from any Poisson homogeneous space into the variety of Lagrangian subalgebras that somehow classifying these spaces, and this variety of Lagrangian subalgebras, in fact, itself has a natural Poisson structure. And this is the Poisson structure that was introduced by Evans and Liu. And with respect to this Poisson structure, all of these maps will be Poisson. And so we'll be able to think of this variety of Lagrangian subalgebras as a kind of universal space of Poisson homogeneous spaces. So I'm going to briefly explain how to produce this Poisson structure, and then we will specialize to some particular cases of the algebras D, including G plus G, which we were just looking at, and we'll see how the wonderful compactification appears relative to this Poisson story. So in order to say what this Poisson structure is, so the dual of the D algebra of the algebra D, I can identify just with U star cross U. And then I have a natural map, which is usually just denoted sharp, that goes from D star to D, that takes a pair XCX and flips XC. Now I want to define a two tensor in the wedge squared of D by the following formula. So this is in the wedge squared of D, which means that it eats two elements in D star, C1, X1, and C2, X2. And it outputs C2 applied to X1 minus C1 applied to X2. So this is something that looks like a classical R matrix. And because, so let me first say that it's an exercise on the problem sheet to show that the Schouten bracket of R with itself. So this is just the bracket induced by extending the Lie bracket on D to wedge powers of D in the usual way. When I apply it to three elements F1, F2, F3 of D, what I will get is the pairing of F1 with the Lie bracket of sharp F2 and sharp F3. And now we have this element in wedge squared of D, and we see that if I take my my algebraic group, integrating D, the action map of D on the Grassmannian, we said descends, restricts to a map of D on the variety of Lagrangian subalgebras. And then I get an infinitesimal action, we call it rho, from the Lie algebra D to global sections of the tangent bundle. Oh, maybe, let me say Grassmannian here. Of the tangent bundle of the Grassmannian. So every Lie algebra element D is going to produce a vector field on the Grassmannian. And in particular, my 2 tensor R is going to produce a bivector field. I'll call capital pi. So this is the section of wedge squared of this tangent bundle. And one can prove, again, all of this entire construction is due to Evans and Liu. One can prove that for any Lagrangian subalgebra, so for every point in my variety capital L, the Schouten bracket of capital pi at that point vanishes. This by a direct computation. So what happens? Well, because pi is tangent to the d orbits on the Grassmannian coming from the action of d on the Grassmannian. It is tangent to the variety of Lagrangian subalgebras, which is a d-stable subvariety of the Grassmannian. And also along the subvariety, the Schouten bracket vanishes. So this means that pi induces a Poisson structure on LD. And the d orbits of the orbits of this action of d on the variety of Lagrangian subalgebras are going to be Poisson submanifolds relative to this structure. So I wrote this all down, but I swept a few things under the rug. And one question that someone might ask right now is, I thought that LD was a singular subvariety. So what do I mean by this statement? So really, you should, if you like some algebraic geometry, you should read this as saying something like, because pi is tangent to these d orbits, when I think of pi as a biderivation, it preserves the ideal sheaf that cuts out this closed subvariety of the Grassmannian. And then this means that it's going to induce a Poisson bracket on the structure sheaf of the subvariety, which on the smooth locus is going to just be a tangent bivector, but it will still make sense to say this on the singular locus. Any questions?
Is a subalgebra and this star is a subalgebra, or could it be just a version?
I think for this, it's important that everything is a subalgebra. Because
depend a lot on which decomposition it should.
yeah, so different Lagrangian splittings will produce different Poisson structures. And I think there's so there are some, actually for various examples, there are classifications of Lagrangian splittings. I think for G plus G, for example, and for some other examples that I'll give. And then you can ask how to what extent these lead to equivalent or non-equivalent Poisson structures, but I don't know of any like complete answer to this question. Yeah, so let me state theorem. So theorem says that now the variety of Lagrangian subalgebras is equipped with this Poisson structure capital pi. And theorem says, first of all, that when I act by the Poisson Lie group U, this action is Poisson. So the action map is a Poisson map. And part 2 of the theorem says that every U orbit on L is a Poisson submanifold. And this means, in particular, in view of part 1, that every U orbit on L is a Poisson homogeneous space. And part 3 says that, moreover, when I pick a Poisson homogeneous space M pi and I construct this Dernfeld map, this Dernfeld map becomes a map of Poisson spaces. So for any Poisson homogeneous M pi, the map P from M to L is Poisson. So in this way, we've produced a Poisson structure on this like target space that classifies Poisson homogeneous spaces, so that when we send the Poisson homogeneous spaces into L, the map we use to send them is actually a Poisson map. And in fact, in many examples, this map is a local diffeomorphism. So we can think of this variety of Lagrangian subalgebras as, being made up of U orbits, which are kind of local models of Poisson homogeneous U spaces. Any questions? Mm-hmm. Mm-hmm. Yeah, so this variety L, this is in principle a potentially singular algebraic variety, but I still have a well-defined notion of what is the Poisson structure on a singular algebraic variety. And using this well-defined notion, I can put a Poisson structure on this space. But the U orbits inside L are always smooth submanifolds, because they're just the orbits of the action of this Lie group. So here nothing funny is happening because of the singularities. And here the statement is also a statement that makes sense, because this, of course, this might be singular, but on the algebras of functions, I have brackets, and I can always say that this is a Poisson map if it preserves those brackets. Any more questions? I think it might be. I haven't checked this, but I was actually talking to Sam Evans about this a little while ago, and this is how I thought about it. And I think it is probably a quasi-Poisson structure, looking at this bracket. But it seems to be that way. We have to think. Okay. Okay, so I want to finish by giving some examples of varieties of Lagrangian subalgebras that people consider, and then circling back to our original examples of these wonderful compactifications to see how they appear here. But I'm going to start. That will be the last example, and the first examples will just be examples. So first example. Suppose that D is just a semi-simple complex Lie algebra. Of complex dimension n. And then I can view it as a Lie algebra over R, in which case it will have real dimension 2n. And on G viewed as a Lie algebra over R, I can take the bilinear form, which is the imaginary part of the killing form, and this is a non-degenerate symmetric invariant bilinear form on G. And then from all of this data, I have an Iwasawa decomposition. Where the first factor K and the second factor, let's maybe call them, what do I want to call them? U and U star are Lagrangian splitting. And then by way of all this stuff, this tells me that I have a Poisson structure on the variety of Lagrangian subalgebras of G viewed as a real Lie algebra. And the geometry of this Poisson structure is basically completely described in the paper of Evans and Liu titled Variety of Lagrangian Subalgebras 1. Okay, so a second and less tractable example is when G is a, maybe for now it can be any Lie algebra. And then I can take D to be, or first, let me say, then I can view G star as an abelian Lie algebra, so I can put on it Lie bracket 0. And then I can look at the Lie algebra formed by taking the semi-direct product of G with G star. So in this product, G can bracket with itself, G star brackets with itself to 0 on everything, but then G acts on G star by the adjoint action. Okay, and in this case, what do I want to say in this case? Here's a, move my arrows. I can define on the space a bilinear form by taking two pairs x1 c1 and x2 c2 and outputting c2 of x1 plus c1 of x2. And this is non-degenerate, symmetric, and invariant with respect to the action of the group, which is now an integration of G semi-direct product with G star. And this, all of this data gives me that the splitting of D into G and G star is itself a Lagrangian splitting, because G and G star with respect to this product are Lagrangian subalgebras. Lagrangian splitting. So this gives us a Poisson structure again. On the variety of Lagrangian subalgebras of G semi-direct product G star. But now this variety and the Poisson structure are like extremely mysterious. So, so in the case where G is semi-simple complex Lie algebra, which is itself an extremely interesting and also mysterious case. I think not that much is known about this, but one thing that is known is that closed G semi-direct product G star orbits on this variety are classified by combinatorial data called abelian ideals inside the Borel, classified very recently, so maybe like 2020 by Evans and Lee, as in Liu, who you saw yesterday in the problem session. Okay. And third example, which is the sort of example that we've already encountered and that motivated this discussion today, is when G is a semi-simple complex Lie algebra, and I take D to be G direct sum with G. So now the two factors commute. And this integrates to the direct product of G cross G, where G is the group integrating factor G. And then the inner product looks like I take two pairs, x1, x2, and y1, y2, and I do killing form of x1, y1 minus killing form of x2, y2. And this is the inner product on G cross G, with respect to which we saw that the fibers of our log cotangent bundle were Lagrangian. I can write a Lagrangian splitting of G cross G with respect to it as the sum of diagonal subalgebra, and then this thing which is usually denoted G star standard. So this maybe appeared yesterday in the problem session. So this is the subalgebra that we already saw earlier today of pairs in B and B minus with the same component in the maximal carton. And with respect to this, with respect to this, we get a Poisson structure and the variety of Lagrangian subalgebras of G plus G. Remember that all G cross G orbits and G diagonal orbits are Poisson submanifolds. And in particular, so here we have, what do I want to say about this? We have maybe two examples of such Poisson submanifolds that are particularly interesting to us. One is the example of the wonderful compactification, which I obtained by taking the G cross G orbit of the diagonal subalgebra and the splitting, and then taking the closure inside L. So in this way, the wonderful compactification gets a Poisson structure from this G cross G action. And maybe what do I want to say about it? And the second example that I want to give you is the following to tie into the first lecture. So a second example of interesting Poisson submanifolds of this variety of Lagrangian subalgebras is when I take an algebraic involution of the Lie algebra G. I can use it to define a subspace, an n-dimensional subspace that lives inside the Grassmannian of n-dimensional subspaces of G plus G just by taking its graph. So I'll call L sigma of pairs X, sigma of X in G cross G. And it's an exercise to show that L sigma is a Lagrangian subalgebra. So this lives as a point in here. And if L sigma is a Lagrangian subalgebra, then I can take its G diagonal orbit, which will be a Poisson submanifold of this variety of Lagrangian subalgebras. And this is going to be isomorphic to G modulo G sigma, at least when I good. So I choose here, I want to choose the trivial center group to be the one integrating my Lie algebra. So this is a homogeneous space inside this variety of Lagrangian subalgebras, which is a Poisson submanifold. And when I take its closure, I will get a compactification of this homogeneous space. And this compactification will be exactly wonderful compactification defined by Becconcini and Processi. And it will have a Poisson structure that extends to the boundary because I took the closure of a Poisson submanifold in a larger Poisson space. So in this way, we get Poisson structures on all these Becconcini-Processi compactifications, and they all live as Poisson submanifolds in the space of Lagrangian subalgebras. Okay. So I think time is up, so I will stop there.
Questions? Questions about this lecture or any of Anna's 4 lectures? Now is the chance, your last chance.
No, this is a compactification of a symmetric space that is smaller than G. Yeah. So in my original like preamble to these lectures, it said that the way these wonderful spaces were first appeared is as compactifications of symmetric spaces.
Any questions online?
On the group, you mean? It's not the Poisson Lie group structure. It's a structure that's induced by this infinitesimal action of G cross G on the group using this 2 tensor R that I defined earlier. I don't know if it has. I think it has some interpretation as like a quasi-classical limit of something quantum, which if I try to say, I'll probably say wrong. But otherwise, to me at least, it's not a structure that's familiar from somewhere else. But it is very, and so all of this is like completely laid out in Evans and Liu, and many things are characterized in a lot of detail. So for example, the symplectic leaves here, at least like torus orbits of symplectic leaves, are like very explicit. And I'm happy to talk about these after. No, because there is no open dense symplectic. So in fact, it's I think maybe so here this is, whoops, you know that G cross G orbits are Poisson submanifolds, but also G diagonal orbits are Poisson submanifolds. So G diagonal orbits on the copy of G sitting inside the wonderful compactification are just conjugacy classes, right? So conjugacy classes are Poisson submanifolds, but they break up into symplectic leaves. And for example, there's a one kind of special conjugacy class of any group is something called the unipotent cone. So you take like all the unipotent matrices, and this is the closure of a single conjugacy class. And that has a Poisson structure, which is generically, I think, symplectic, but it's a singular variety. So in the boundary, I don't think there's any other log stuff in here.
Any other questions? If not, let's thank Anna not only for this talk, but for her